Right. Welcome to the Competitive Algebra Seminar of IIT Bombay. We are very happy to have Mitsuhiro Miyazaki from Department of Mathematics, Kyoto University of Education, Japan. And he will give two lectures on Hibi rings and Ehrhart rings of chain polytopes. During the lecture, you may ask questions in chat box. At the end of the seminar, we will have a live question answer session. So, Mitsuhiro, you are welcome to begin your lecture.
Thank you. First of all, I'd like to thank the organizers to give me a chance to talk in this seminar. In this first talk, I'd like to recall basic facts and basic notions of Hibi rings and Ehrhart rings in general, and Ehrhart rings of order and chain polytopes. So this week, Hibi's okay. Yes, Hibi's paper and recall and other papers concerning that Hibi rings. Next week, I'll talk about my recent results and myself, and with joint work with Janet Page on the canonical models of Hibi rings and the Ehrhart rings of the chain polytopes. So let's start. First, I'd like to state the notation, fix the notation. For sets x and y, I denote x to the y, I denote by x to the y the set of maps from x to y. And we denote, when x is a finite set, we denote R to the x, by R to the x, the Euclidean space. Usually, if R to the n elements A1 up to A to n is considered a map from I maps to AI. So I don't usually, I don't mention the, I don't mention and correspondence between the set of integers to the finite set X. So I use this notation. And for Gzai 1 and Gzai 2 in R to the X and A in R to the AR, we define map xi by xi x equals to a times xi x, and xi 1 plus minus xi 2 is defined by adding values of xi 1 and xi 2. And for a subset, In the following, I assume that X is a finite set. In the following, if A is a subset of X, we define the characteristic function chi A by the value of X is 1 if X is in A, and the other case, the value is 0. And next, I did define the terminology of poset. If I don't mention, the poset is always finite. A chain in Q is totally ordered subset of Q. The length of a chain C is the number of elements of C minus 1. The rank of Q is the maximum of length in chain of chains in Q, and if every maximum in inclusion relation, in terms of inclusion relation, and if every maximal chain has length rank Q, we say that Q is pure. And for a subset I of Q, I is a poset ideal of Q if I is closed, if and only if I is closed below. That means any element which is smaller than an element in I, then it is contained in I. Now, if x and y are elements of Q, and x is less than y, and no element between x and y, then we say Y covers X and denote X dot Y. And if X is less than or equals to Y, then a sequence of elements by covering relation then with this form, covering sequence of relation with covering form of this type, then the Z0 up to ZT is a chain, and we call a saturated chain. From X to Y. Now, we extend opposite. Minus infinity is a new element which is not contained in Q. Then we set Q equals Q minus is the set attached from Q to Q and minus infinity. And X is less than Y in Q minus if and only if X and Y are elements of Q and less than X is less than Y in Q, or X equals to minus infinity and Y is in Q. And we define Q plus, that is plus infinity, adding plus infinity to Q and define order similarly is defined. And Q plus minus equals to adding both plus infinity and minus infinity. I forgot one definition. And for Xi in Rx and B is a subset of X, I define Xi plus X to be the sum of values of elements in B. And Xi plus empty set is defined to be 0. And we define order unchained polytope. Let P be a poset. Finite poset. OP is the elements of the Euclidean space Rx such that the values are all between 0 and 1 for any x. And if x is less than y in P, then fx is greater than or equals to y in R. This is that is weakly reversing function. In fact, Stanley's definition of order polytope is weakly order preserving, but in incoherency, in order to coherent Hibi rings, I define reverse way. This is not this. The polytope is symmetric, so it is not important. It is we don't have to care. Another polytope, CP, is elements, the set of elements of Euclidean space, which is non-negative for any coordinate, and F plus C is less than or equals to 1 for any chain C in P. So one point is also a chain. So it is of course the value fx is of course up upperly bounded by 1. Then we call OP the order polytope. And CP the chain polytope. Next, we recall the definition of Ehrhart rings. Let X be a finite set. And let P be a rational convex polytope. That is, all the vertices are in Q to the X. All the vertices are rational points. And let K be a field. And I also use here minus infinity, a new element, because later I use this notion by substituting x to p. So minus infinity is coherent, consistent for later use. Which is not in X. And Tx is a family of indeterminates indexed by x minus. Oh, I forgot to. X minus equals to x and Tx is a family of indeterminates indexed by this x minus. And for element of r to the x minus are known z to the x minus. We set t to the f equals to product of tx to the fx. X run through all the elements of x minus, which is an element of Laurent polynomial ring, which is a Laurent monomial. Then Ehrhart ring EK over P, Ehrhart ring of P over a field K is defined as follows, which is generated by T to the F, where F is Z to the X minus 1, and F of minus infinity is positive, and 1 by F of minus infinity times F is in the polytope P. And EKP is called the Ehrhart ring. Of P over K. And we set degree of T minus infinity equals to 1 and degree of Tx equals to 0 for any x. Then EKP is an n-graded. I use bold n as the set of non-negative integers. Now, let me show this notion by a picture. Consider here the polytope is like this. Then one add new axis in t to the minus infinity, new axis, and lift this polytope P to 1 above, and consider the convex polyhedral cone generated by this lifted polytope. Then consider all the integer points in this convex polyhedral cone. All the integer points in this convex polyhedral cone. Then EKP is the affine semigroup, the monoid algebra over K consisting of monomials corresponding to these all the integer points in this convex polyhedral cone. This is the Ehrhart ring of P. And important facts. Since P is rational, EKP is Noetherian. And by the result of Hochstar, normal, Cohen-Macaulay. And of course, since it is a subring of a Laurent polynomial domain, it is a domain, and with canonical module, by the Stanley's description of canonical module of a normal affine semigroup, we see that one by f minus infinity times f is contained in relative interior of P. Relative interior means interior in the affine space affine space spanned by P. Hochstar's result, Stanley's description of canonical module is that the integer points in integer points in the relative interior of this convex polyhedral cone is the canonical module. Then, but this is I forgot the important thing. And so this corresponds, this T to the F, this F corresponds to relative interior points in this convex polyhedral cone. So by the Stanley's description of the canonical module in of affine semigrouping, we see this. So, and for main focus of the talk is the Ehrhart ring of order and chain polytopes. But by Stanley, it is known the Ehrhart rings of order and chain polytopes. have the same Hilbert function. Now, we go to the definition of Hibi. Let D be finite distributive lattice. This lattice is a poset who with for any two elements there's sup least upper bound and greatest lower bound for any two elements. This upper bound is written as A alpha join beta, and we call join of alpha and beta. And greatest lower bound is written this way, and we call the meet of alpha and beta. And let P be the set of join irreducible elements of D. That is the set out of alpha in D, which cannot be written as a join of different elements of beta and different elements of D, and D alpha is not a minimal element of D. Then let script IP be the set of poset ideals of P. Then, by the structure theorem of Barkov, and it is also verified easily as an exercise, like an exercise, that D and IP is isomorphic. We can define an order relation by inclusion on IP. Then for any alpha, for element alpha in D, we correspond this poset ideal of B. And if a poset ideal I is given, then we correspond an element D, which is the join of all the elements of I, and for empty set, the minimal element of D. Then, it is an easy exercise that this is one-to-one correspondence. And Hibi showed now here. Let X alpha be a family of indeterminates indexed by D. Then X alpha, the polynomial ring divided by this binomials X alpha meet beta, X alpha join beta, and alpha and beta are incomparable in the order of D is normal Koyama-Koren ASL. I don't mention the definition of ASL today. Domain over K on D. Hibi's idea is consider a map let Tx x in P minus be a family of indeterminates. Then consider map. We identify D and we identify D and IP by this relation, by this correspondence. So I write X alpha as Xi if I and alpha are corresponded. Then Hibi's idea is consider a map phi to the polynomial indexed by P minus, and Xi is mapped to the monomial T minus infinity times product of X in I Tx. Then by Xi, Xj equals to T minus infinity squared times this is equivalent to this part is identical to T to the chi I. Characteristic function, chi is characteristic function, and T to the chi I times T to the chi j, and this is equivalent T to the chi of I cap j times T to the chi of I cap j. This is phi of I cap xi x of I cap j times x of I capture. So this part is in the kernel of phi, and it is rather easily verified that uh, image uh, kernel of phi is xi xj minus xi cap j xi cap j. I and j are not comparable. And Hibi called image of phi RKD, and this is the Hibi, nowadays called Hibi. But recall the definition of order polytope. Then RKD is exactly the Ehrhart ring of the order polytope. And so Hibi's notion, probably Hibi wanted to analyze ASL structure over various posets, but and constructed this RKD, which is now called the Hibi ring. But Hibi ring itself is a very important object, and it is identical to the Ehrhart ring of order polytope, which is defined by Stanley. Stanley showed various similarity of order and chain polytopes, such as they have the same Hilbert function, other than other. I introduced today here the Hibi and Leeds rather recent result. So that is EK, the Ehrhart ring of chain polytope. EKCP is also an ASL over D on D, ASL on D. So recall this fact. This is also Stanley. EKCP is generated by T of chi A cup minus infinity, and A is an antichain in E. A is antichain means for any A, B in A, A and B are not comparable in the order of P. And Hibi and Lee showed that the chain polytope EKCP is also an ASL over K on IP, the set of poset ideals of P. The points is there is a one-to-one correspondence of poset ideals of P and anti-chains in P by for a poset ideal I, one consider the set of maximal elements of I, which is of course an anti-chain. And for an anti-chain is given, if an anti-chain is given, then one corresponds the poset ideal generated by A, that is X in P, X is less than or equals to A for some A. And of course, empty set. Now, consider I1, I2 are poset ideals of P, and set A1 equals to maximal elements of I1, A2 the set of maximal elements of I2. And this is the point. Script A, let script A be the union of A1 and A2 as multisets. And B1 equals to maximal elements of script A, and B2 equals to A minus maximal elements of A. Then B1 and B2 are usual sets. No usual sets. And Ji, let Ji the poset ideals. Generated by Pi respectively. Let me explain this by example. Let P be a poset with Hasse diagram, this, and I1 is poset here, and I2 is poset of poset ideal. This here. Then maximal elements of I1, maximal elements of I1 are these 3 points, not A2, A1. And maximal elements of here, I2 are these 2 elements. So consider this multiset and take maximal elements of this multiset. Here, this is B1, and this is B2. And J1 and J2 are poset ideals generated by B1 and B2 respectively. So yeah. J1 is here, and J2 is here. So and psi be the map from the polynomial to another polynomial indexed by p minus. And xi is mapped to t minus infinity times chi of t to the chi of maximal elements of I. Then psi of chi x1 times chi x2 equals to t minus infinity squared times t chi t of chi maximum elements of I1 t of chi max I2 equals to t minus infinity squared max j1 times t of chi max j2. Note that maximal element of j2 are these 2 elements, and maximal elements of J1 are these 3 elements. So since as a multiset, A1 cup A2 and B1 cup B2 are identical, this equation holds. And this is psi of xj1 times psi of xj2. Thus, it is easily verified Hibi and Lee denote J2 equals to I1 star I2, and note J1 equals to I1 cup I2. This is very easy fact. And kernel of psi is generated by this, and image of psi is the Ehrhart ring of chain. So this is EKP. So EKP is an ASL over K on IP. Finally, I recall the Gorenstein property of Hibi rings. The Hibi ring, RKD, which is identical to the Ehrhart ring of order polytope, is Gorenstein. If and only if P is pure. And as a corollary, the chain polytope, the Ehrhart ring of chain polytope is Gorenstein, if and only if P is pure. Because Ehrhart rings of order and chain polytopes have the same Hilbert function, and by the Stanley's result, graded Cohen-Macaulay domain is the Gorenstein property of graded Cohen-Macaulay domain is characterized by Hilbert function, or should I say H vector is symmetric. So since these two rings are also graded Cohen-Macaulay and have the same Hilbert function. One is Gorenstein if and only if the other is. So I end the talk of today. Thank you.
Thank you very much, Professor Miyazaki. We will take questions. Are there any questions? Yeah, if the polytope is not pure, can one describe the components of the canonical ideal?
Yes, that's the point of next talk.
Okay.
I described in the poset in these papers.
Okay.
I described the generators of posets, generators of the canonical module. Canonical module is described by standards description here. I describe in combinatorial words the generators of this canonical module.
Okay.
That's the point of next,
Okay.
next talk.
Yeah. Thank you.
This first, sorry for elementary talk this week, but the first, my plan is the first talk is I want to fix notation and recall basic facts of Hibi rings and
Okay.
order and chain polytopes and Ehrhart rings.
Right. Okay. Are there any questions? Okay, so if not, we will close the seminar today and meet next time for the second seminar of Professor Miyazaki. Thank you very much.
Thank you.
Thank you.